Hi, my name is José Enríquez, and I'm the CEO and founder of 𝗘𝗀𝗺𝗺𝗺𝗺, a digital platform whose mission is to connect the fiber optics ecosystem and bring light to every home in the Americas, from Alaska to Tierra de Fuego. Today, in this webinar series, we have a very interesting subject: how to stretch the limits of PON networks by deploying novel splitting structures. This will be presented by Erick Pennings, who currently is Business Development Director at Ensure. Okay. So Erick, the stage is yours. Please go ahead, and everybody, welcome to this series of TFO webinars. I'm recording.
Okay, well, thank you, José, for the introduction. So a very warm welcome to the entire audience. So that means good morning for the people in South America and North America. Good afternoon for the participants in Europe, and of course also a good late evening for the people in Asia. So let me pull up the presentation. Here we go. So the presentation is connectivity to you, and then how to stretch the limits of PON networks by deploying novel splitting architectures. And in the presentation, we will have three different parts. So we start with the overall goal of why we are all together here. And that goal, in our view, is to create together a more interconnected planet with all the online ordering, remote working, and staying in touch with each other. But that interconnectivity needs to be robust and it needs to be dependable. And that brings us to the question of how to create that robustness and how to actually get products that have a high quality. Then the second topic in the webinar is the role of integration, especially integrated optics. So photonic integrated chips can really help to make the networks more reliable. But in addition, these chips can also be custom. So since we have the PLC wafer fab ourselves, we can make custom chips for our customers. And in this way, we develop the asymmetric chip. And this is exactly what can help the PON networks. And this brings us then to the third topic of the webinar. We increasingly see that PON networks are running into limits, either losses, short of fiber, the increasing bandwidth can cause also limitations. And we will be presenting 4 use cases where the asymmetric splitters have been able to bring the solution. So what is bringing all of us together here? At a shared goal between all of us that are here now on the call is that we want to make this a more connected planet. Especially during the last 3 years, we've seen that the ability to work remotely, to do all of our grocery ordering online, to have social media, to stay connected with family and friends is very important. But it's not just about this connectivity, it is what we call premium connectivity. These days, internet is a must. It must be reliable and accessible at all times, and it has therefore become essential. Now, the connectivity has been built by fibers in combination with integration, and that integration is both electrical with ICs, but also with optical ICs. And the combination of these fibers together with the optical and electrical integration has allowed the internet to grow in the way that it did. But then the last mile here is still a critical part. This is where not only most of the cost is, because the cost is in the digging and the permits and the right of way, and the cost of digging often dwarfs the cost of the equipment. But this is also where, amplifiers may fail, where fibers can be cut and so on, and it's often unprotected. So that last mile in that respect is critical. So the question then is, how can we make this connectivity, which is so important for all of us, premium? Well, one thing is already very important, that with PON, we have a passive infrastructure, which is a big improvement over the previous electrical infrastructure where amplifiers could fail. So the fact that it's passive really helps. Additional, of course, we need to prevent fiber breakage, and we can do that to a good degree by putting the fibers underground. But then the last thing is that, and this is partly our contribution here, that we want to make the components also premium. In the past, with, say, a cable TV network, if the TV would not work for a few hours in the evening, then at least the kids could do their homework. But today, if the Wi-Fi is failing, then there is a shout from the kids upstairs that the internet is not working. So it's much more critical right now. So how do you do this premium or quality? And I'm showing here two cars, actually two cars that I owned myself. So the Saab on the left hand and a BMW, a second-hand version, of course, on the right-hand side. And the importance of the example is that they're both high-end cars. Both Saab and BMW are ISO 9000 certified. Both cars are completely reliability testing. At the same time, with the Saab, I was almost at the garage every week. And with the BMW, I called the garage after a year, and he said, "Mr. Pennings, you're not supposed to come here within 2 years. We only service the car every 2 years." And there was actually no repair whatsoever needed in between. So there can be enormous differences in quality, even if there's ISO 9000 certification and complete qualification. So what then is the key here? In our view, the key next to ISO 9000 and Concordia is vertical integration. Only if you have complete control over the entire supply chain can you well guarantee the quality. And this is, for example, also the reason why companies like either Tesla or Swiss watches are very much vertically integrated. And next to vertical integration, there's also a dedication to premium in the sense of investing in equipment as well as in customer support. Yeah, so at Ensure, our main products consist of splitters, demultiplexers, ferrules, other passive components and closures. And we also acquired a new company that makes EDFA modules and modules for sensing. But yes, next to ISO certification and Concordia, we have invested in premium, and we are fully vertically integrated. So we have our own PLC fab. We make our own thin film filter coatings. We make our own in-house ceramic ferrules, as well as the enclosures. I'd like to show now a brief video. So we care about making a good number of videos, because this is, without traveling to China. Unfortunately, you can do this right now again. But before the last few years, it was really difficult to go there with the pandemic. But it is really very instructional to see, to actually get a virtual factory tour.
Welcome to Ensure. Premium connectivity solutions that help you meet the insatiable growth of optical networks. Let's take a closer look. Our laser precision ceramic ferrules have high concentricity at both ends. Our extrusion and machine processes guarantee it. Ensure signature PLC splitters can be crafted with various bandpass, splitting ratios, fiber types, and connector and packaging options. We innovate and manufacture customized passive network components. including solutions for advanced FTTX applications. We offer a full package of WDM products for core, metropolitan area, and access networks. Ensure offers integration and assembly of your components, all within our facility, saving you time and money. We can also produce white label design and packaging, putting your brand on our best-of-class products. So what's in our secret sauce? We invest heavily in specialized equipment, taking great pride in our ability to manufacture our own PLC wafers and chips. We've perfected complex industry-leading processes in our labs, like plasma-enhanced chemical vapor deposition, inductively coupled plasma, oxide deposition, UV photo, and ultrasonics. But what really sets us apart? We control the manufacturing process from start to finish, with an unwavering attention to detail. Since we control the entire production chain, we have the ability to scale and adjust to meet your specific requirements. Ensure's steep investment in R&D and quality control keep us ahead of the pack. Our highly specialized engineers and technicians develop innovations that quickly become the benchmarks of our industry. And when it's time to ship your order, you can expect reliable, pristine components right on time, anywhere in the world. Ensure, building bridges to an ever more connected tomorrow. Be sure to visit our website for a deeper dive and give us a holler to let us know how we can partner in your success.
Okay, so let's continue with the slides. So this is one example of what you can do when you're completely vertically integrated. This shows an example of a 1x4 splitter where the customer wanted an access insertion loss of only 0.5 dB on top of the 1x4 splitting loss, the 6 dB. And we were able to do that by combining grade A connectors together with a PLC chip that we could screen for minimal insertion loss. And so in the end, we were able to meet the requirement of the customer, but that was only possible because we controlled the entire component. But then there's something else about quality. So in the case of the cars, what should I have done if I had wanted to know the differences in quality between the Saab and the BMW before buying them, actually? And the answer to a good degree is to simply ask other people who already own a Saab or BMW about their experiences. So that's where customer referrals come in. And this is a statement, for example, from Vodafone, who indicates that their decision to use Ensure is largely driven by our adherence to strict manufacturing standards and ongoing quality. But it's not only Vodafone. This is an example of Telefónica, where their homologation went a lot further than the regular Telcordia GR1221. And we completely passed that. And as a result, are the official supplier of Movistar. And in addition to Vodafone and Telefónica, there's a large group of other customers. Before we move to integration, are there any questions about quality? So what I wanted to convey is that quality is important in access networks and that it is not so trivial how to exactly do that. But are there any questions from the audience on kind of the quality part of the presentation? If there's no questions right now, let's move then to photonic integration, which is the second part. So photonic integration is really important here for two reasons. The first one is that it actually not only can reduce the size of components and the cost of components, but it actually has also a critical part in this reliability story. And secondly, it leads the path to the solution, the asymmetric splitters that can help you to overcome limits. Now here you see that in a PON network, there's actually now only passive fibers, which should be completely okay, provided you do not break them. But the only critical part now is the splitter. And the splitter is shown here. This is the PLC splitter itself, and here's all of the connectors, which explains also our decision that we wanted to own the PLC fabrication process by having our own fab, as well as the ability to make all of the connectors ourselves. So photonic integration works similar to electronic ICs. It helps to reduce the size, cost, and it improves the reliability. If you take a 1x64 PLC chip, it actually replaces 63 separate 1x2 splitters and therefore reduces enormously the total number of components. Photonic integration is now getting very popular because, for example, also in the data center, there's now a lot of photonic integrated circuits that are being used, which is mainly silicon photonics, but PLC actually is a material system that already has been around for at least 20 years. And so it is the first photonic integrated circuit that actually has been deployed on a large scale. Now, what is sometimes not well understood is that the PLC wafer fabs are very strategic. There's only a handful, maybe about 10 PLC fabs in the world. You can buy PLC splitters from a much larger number of companies, maybe some 40 or 50 even. But there's only about 10 or so PLC fabs, and most of them are actually in Asia. And then out of this number, many are actually focused on the data center, but only a few are truly focused on fiber to the home, and we own one of these PLC fabs. So important. Here you see on the left hand a gray. You remember, of course, from the James Bond movies. And from the outside, it looks really nice. But if you look at the inside here in the middle of this gray supercomputer, it's a horrendous number of wires. So all of these microprocessors are actually interconnected, and many of these wires are hand soldered. And if one of them breaks, then the supercomputer will not work. And in the data center right now, you see something similar, where everyone, of course, knows these Google-inspired data center pictures, which have all these blinking lights. But if you look at the backside of this rack of servers, then it's going to be a spaghetti of fibers. And if you then look at this PLC chip here on the right, if this is a 1x64 splitter, it actually can replace 63 1x2 splitters, and in that way enormously reduce the number of components and interconnects, and thereby it also makes it much more reliable.
Eric,
yeah.
Here there's a question from Miguel Chavez, and the question is, please, how do splitters work internally?
Oh, yeah, that's a good question. Thank you, Michel. So the
Miguel.
Oh, Miguel, sorry. My pronunciation is not Miguel. So what you see here is that there is, so this is the input fiber. The input fiber is coupled to the chip, and this is the splitter chip altogether, the brown part. And it first has a 1/2 splitter, which is a wide junction splitter. So you can make that in multiple ways, but this is a wide junction splitter, which is popular for PLC. If this were silicon or indium phosphide, you would use a different type of splitter. And here is a similar wide junction 1/2 splitter, so that the input is divided equally over 4 outputs. And by adding another stack, you can make it a 1/8, and another stack, you can make it a 1/16, and you can continue in that fashion. And then this is a fiber V-groove array, often silicon with grooves in it. And here you have, say, 4, but also 8 or 16 or 32 fibers. And you couple the chip to that V-groove array. That needs to happen very accurately and very robustly. But in that way, the light from the input fiber is split in 4 equal parts in 4 output fibers. Miguel, does that answer the question? Okay, I think we can continue.
Yes.
So then, now the fact that we have our own wafer fab allows us to not only make, good PLC splitters and make them low cost because we do it in our own fab, but it also allows us to make a custom chip in the same way that you can also do that at the TSMC. And in this fashion, we developed the asymmetric splitter for a particular customer, but in such a way that, of course, now we can offer this to anyone. But yeah, if you would have particular needs, you can come to us and say, we actually need a splitter in this fashion, or we want a different functionality, and we can do that for you. But in this way, we also did the asymmetric splitter. And that basically takes us then to the last topic. That's the limits in PON networks and how the asymmetric splitters can be used in order to stretch or solve those limits. So I think we're all familiar with the fact that there are increasingly limits in PON networks. So one is, of course, fiber shortage. So the biggest cost in PON networks is actually the digging and the fibers, and much more than either the passive components or the electronics in the central office or in the home. Then, of course, the incumbents often do have fiber, but the new carriers are often short. And if they are short on fiber, then they may have to lease dark fiber, and that can be very expensive. And the other problem is, of course, especially in rural areas where either there's no fibers, and or if you can find fibers, then the topology often does not very well match the PON architecture. The second problem is with link budgets. So what will happen if the fiber is too lossy, or it's just a little bit too long, or you have, for example, a large number of connectors rather than splices? Then you can easily have 1, 2, or 3 dB extra insertion losses, and you simply won't have sufficient power. And this does seem to happen much more often, because what's popular is also the plug and play. So with a shortage of people that are trained to do the installation in the field, carriers often rely more on plug and play, which means that they use robust outdoor capable connectors of putting everything together. This makes it a lot easier to get everything connected, especially if installers are short, but you will have larger insertion losses. And the last topic I heard about recently, so of course GPON was initially designed for 64 users, 20 kilometers, and 2.4 gigabit downstream and 1.2 gigabit upstream. But now we're having 10 gigabit, and in standardization organizations, we're already talking about 25 and 50 gigabit per second. And at those higher bit rates, the budget may not always work anymore, especially at 50 gigabit, and it all needs to be backward compatible. Then you're simply short in power. And then there's also backward compatibility. So initially it was GPON, but if you have XGS-PON, then it needs to be put on top. So you need to insert an additional filter to put them together on the single fiber. But that also has an additional insertion loss. And this all leads to a problem. And we feel that the asymmetric splitters can be a great tool in order to overcome many of these limits, and we'll explain to you in more detail how that works. So this is the PON architectures.
Eric, sorry to interrupt you.
Sure.
Marino Quiñones is asking, fiber loss applies for blown fiber or for polyfiber or internally on the cable. I'm not sure that is related to the splitting.
Yeah, can you repeat the question, please?
Sorry, I am Marino Quiñones, but I did not have that question. I don't know why it's my name on that, but I already have a question regarding to the DWC splitters.
Yeah.
I have the opportunity to work with them, I think a lot of times. So the main thing that I would like to know is, what do you consider are the main parameters to be focused on in order to have a stability on the losses? For example, let's say that we have an 820 DWC splitter, but when we made the insertion loss testing, it's not stable, the 8% of the power for one of the outputs and the 20% of the power for the other one. I mean, it's a variation that is very difficult to stabilize. But what do you think is the main parameters that we have to be focused on in order to reach that stability that that the splitter it's supposed to have?
Yeah, I think this is a really great question. Thank you. So this is something that is not listed here on this slide, but you are right in the sense that this can indeed be a problem. So often during qualification, you may get mute. Okay, can you hear me?
Yes. Yes.
Yeah, okay. So you may get some, what shall we say, hero samples, ones that are extremely good. But then in practice, you may see that in actual deliveries, there is either a bigger variation, or you can just have bad luck. And then one of the outputs that need to go to a critical fiber has a bit larger insertion losses. And yeah, you can either manage that by more carefully selecting the supplier or the spec, or do incoming inspection. But this is, of course, very time consuming. But this can also be, I think, solved by, what we're mentioning here, by the asymmetric splitters. So the asymmetric splitters can actually give you a lot more room in terms of power budget. You can easily cover several dBs or many dBs of power. And the trick is that for many subscribers, you actually have way too much power. And that's for all of the homes that are actually close. So the problem only comes up for the homes that are really furthest away. And it's there where you need to be careful with the power budget. Yeah. Okay. So if we go to the next slide. Okay. So this is, if you want, the two dominant architectures for PON. So one is the point-to-point. That's not used in most of the world. It's used in a number of countries in Northern Europe, including myself. So here, every home has a single fiber. This is, of course, the most expensive in terms of fiber deployment, because 64 users, in worst case, may each have 20 kilometers. But it is, of course, infrastructure that is future-proof. There's only the fiber, there is no splitting. It goes directly into a Cisco router, and that has advantages, but it is very expensive in terms of fiber deployment. Then what is done in most of the world is, of course, PON, GPON, XGS-PON, etc. And this relies on having a single feeder fiber. This fiber, if this PLC splitter is very close to the homes, then of course the single feeder fiber will save a lot of fiber. But more importantly, it's now also that this single fiber, the 64 users, are connected to a single transmitter, so that the 64 users are actually sharing the more expensive transmitter in the central office. But here comes the point. This works beautifully if, of course, all of the homes are at 64, at 20 kilometers. Then you will save basically all of the fiber, and you have, what shall we say, the best case would be 20 kilometers of fiber only. It would be one long fiber to here, with then a number of short drops. But this is not realistic. In practice, there will, of course, always, it's a distribution with a number of homes far away, but many homes really close to the central office. And in that case, if the first home would be within a kilometer, then in practice, what you're looking at is something that is close to this. You actually are not sharing the fiber. And this then gets to the alternative architecture, which is a daisy chain, or what they sometimes call a tap architecture. In that case, you have a single fiber that goes to the first group of homes. You have a drop to 4, 8, or 16, or 32 users here. And then there is a through fiber that goes to the next group of homes. You have another drop, and then another through fiber for another 5 kilometers, another drop, and then a last drop until the users that are the furthest away. And if you do this well, then this can actually get close to 5 plus 5 plus 5 plus 5 is a total of 20 kilometers of fiber, plus a few relatively short, drop sections here. But if you design this well, they can be relatively short. So this is by far the most efficient in terms of fiber deployment. The last splitter will be symmetric because you don't have a through port anymore. And the key also is that in order to make this well, you need a large number of asymmetric splitters, because for the first one, you want to pass 95%, but only drop 5. Here you want to probably pass through 90%. Here maybe 70%. Because the further you get, the smaller the drop section needs to be in terms of splitting ratio. You see that here again. So this is the normal architecture with one splitter or a few splitters, but then all of the homes, assumed to be at more or less equal distances, so that this is what you can share. But in practice, that close to never truly happens in that way, and a daisy chain architecture with a drop, a drop, a drop will be much more efficient on the fiber. And the splitter in that case looks different. So what we had before with the 1x4 is 1 fiber in and then 4 out. This will be 1 fiber in and then a small tap coupler on the chip combined with a 1x4 splitter. And this is what we then call a 1x5 splitter. And like indicated before, if you want to make this work well, then you need a large number of tap ratios, several different split ratios, and you can do this partly. Some passive suppliers have this in a hybrid form, where you combine a separate coupler with a symmetric PLC splitter chip. But this is clearly bigger, it may be more expensive, and it is less robust than if you can do everything on a single chip. And that's the smallest, and it's the most cost effective. Now we're moving to the second use case, which is an MDU, multi-dwelling unit. So suppose you have a high rise with, say, 10 floors. Then normally what often happens is that you put one 1x64 or a number of splitters in the basement, and then you have 60 or 100 or 200 fibers all going up to the apartments. But this is not efficient. It's simply way more efficient to have a first drop splitter at the first floor, a second splitter on the second floor, then the next floor, another splitter, and so on, so that there's actually only one fiber going all the way up. So this is the same as the daisy chain that you can use in rural areas, but then in an MDU. So this was the original reason that we developed these asymmetric splitters together with a key customer. But what's really interesting is that recently we had a number of customer requests that actually proved to be caused by fiber limitations or lossy structures, and where the asymmetric splitting actually proved to be the solution. So one was a carrier who actually wanted to connect 128 homes using a single feeder fiber. So they had a large group of users, and somehow in order to get to that area, they were only able to get a single fiber, which of course had to be leased, and it was very expensive. So they wanted to cover 128 homes with one feeder fiber. Now, normally this is simply not possible to do because the PON standard was only defined for 64 homes. And so you can also not say, hey, I need 3 dB extra budget in order to cover many more homes. Why don't I specify a splitter with 0 dB insertion loss? Because it's not findable, or it is very expensive. But what you can do is to make an asymmetric coupler here. So if you split this in 40-60 and you use the 60% for the homes that are actually the furthest and the 40% for the homes that are closer, and the difference even does not need to be so large. If, say, the 40% is going to be plenty for all the homes that are within 15 kilometers, and the 60 will be plenty for all of the homes, even if half of them are all at 20 kilometers. So you only need to make it slightly asymmetric, and then it will work. Is there any question on this? Yeah, so then I'll take you to the last example here. So that was actually another carrier that came with a specification for the PLC splitter that was simply undoable. Nobody was able to meet that. But in actuality, the problem was caused by the fact that the network had to be built with maybe 6, 7, 8 different fibers, and these fibers could not be spliced together. They were all interconnected with connectors, and in that way they had 2 to 3 dB too much insertion losses, which I think is similar to the case that you were describing, Miguel. And also here the solution proved to be, so the 3 dB extra loss was normally insurmountable. You cannot specify a coupler that has no insertion losses. And even if you could find it, then it would be unaffordable. But if you make it slightly asymmetric, then it easily works out, because many of the homes that are closer by have way too much power. And if you use a little bit of that power for the homes that are furthest, then you can easily compensate the additional 3 dB losses.
Eric,
so also here,
Marino,
yeah?
if you can unmute yourself, you can ask the question yourself.
Yes, please.
Okay. Yes, I have a question. Why the output with less power has a bigger insertion loss in this case, in this example? The one with the radio of 45% has an insertion loss of 14.5, and the other one has 13.2. But I don't really know why it's bigger, the 45% than the other one.
Yeah, I think you have to read this the other way around, in the sense that this one is passing 55% of the light, and therefore has a better budget than the one that is passing 45%. But it depends a little bit. You may be right in the sense that it is somewhat confusing, because it depends on whether this is the amount that you pass on or the other way around. But the main message is that by this carrier was only short by about a dB or so, and by making it slightly asymmetric, you were able to meet the requirement of 13 dB total budget, and that could be done by only a slight asymmetry. Yeah.
Okay.
Miguel has a question as well. Miguel, you can.
Yeah, but Marino, if you have something like this, then of course do reach out to us. In most of the cases, what we've seen is that you need to let us know what the power budget problem is that you have, and then we can propose a particular splitter configuration that will make that work.
Excellent. Thanks a lot.
Yeah. So what was the other question?
Miguel Acuña?
Yes, that's me. I have a question regarding the loss as well. For an example, usually when we're using a splitter that is 1 × 4, we have a loss of 7.4 dBs, for an example. So when we divide that equally, we say that we have a loss in each line for 7.4 dBs. However, I'm not understanding, when we have this ratio, let's say 30% in one line and 70% in the other line, it means that how can I see that this increment is going to be going? I'm going to still have 7.4 dBs in each line of loss. So how it's going to change? How can I know that?
Yeah, so also here, Miguel, and I hope I now pronounce it correctly, but it's a good example. So normally you would have, say, 7.4 dB insertion loss equally in all of the 4 outputs. And of course, in that case, if you have, say, too many connectors, or the components that you're getting are too lossy, then you can run into problems. But the key lesson here is that in your deployment, not all of the homes will be at 20 kilometers. And if you, if say some of the homes are at 10 kilometers, some at 15, and some at 20 kilometers, then it may make sense to make the splitter slightly asymmetric. In that case, you can, for example, I'm just throwing out some numbers. So then rather than having 4 outputs that are 7.4 dB equal, you could make one, say, 6 dB, one 6.5 dB, one 7 dB, and one 7.5 dB. So of course the 7.5 dB is worse than the 7.4 dB, but the 7.5 dB output, you direct it to all of the homes that are close by. And then the 7 dB one to the homes that are a little bit further, and the 6.5 one to the one that are a little bit further even, and then the 6 dB to the one that is the furthest. But by having 6 dB loss only for the furthest, you actually have gained 1.4 dB and then can just make it work. And for all of the homes that are closer, you're not running into problems because they're so much closer that you actually still have spare budget. Yeah, is that making sense?
Yes, it does. Just what I'm not quietly understanding, it's how can I know if for an example, how much loss I'm gonna have on a 30% output and how much loss I'm gonna get on the output that I'm getting the 70% of the signal, for an example. How can I know the loss of each one of them?
Yeah, so also this is a great question. So right now, what shall we say, in a normal 1/64 splitter, all of the fibers are identical, and that makes it easy to deploy them, but you can run into limitations. But if you make them asymmetric, then, because right now there's so much power wasted, I mean, all of the homes that are closer by are getting maybe 10 dB too much power, which you don't need. This is all thrown away. But if you make it slightly asymmetric, then in this case, we may have to give this a white color, this a yellow color, so that people in the field, know where to direct these fibers to. And so they will need to be labeled. But then if you have, say, WDM in the metro or long haul, these are all WDM, they are individual wavelengths. And so, carriers are used to the fact that, they need to know which fiber goes where. It's just that, this has not been so common in access as it is in metro or long haul. Does that make sense?
Yeah. Yep. Thank
Okay.
you very much.
Any other questions? Yeah, so then I basically take you to the last slide. So we've covered 3 topics here. So with, first of all, interconnectivity being increasingly important. This is the internet age. Quality, in our view, is critical next to size and cost. So, of course, cost, China pretty much is the place to get it at the lowest cost, but you do not only want low cost, you also need quality and you need reliability. This stuff needs to go out in the field and it needs to be there for the next 20 years. And quality is always hard to grasp. What really makes one product more reliable than the other? But in our view, it is the vertical integration that gives us the complete control over the manufacturing process, and that's critical here. But the second thing is that photonic integration also helps. If you make an asymmetric coupler and you put everything on a single chip, it's simply going to be lower cost and more robust, more reliable than if you combine a 1/4 with a separate asymmetric splitter. And it also helps in the sense of greatly reducing the number of interconnections. And then the last is that, we can make custom chips, but in that way, we've also been making asymmetric splitters.
Erick,
Initially, Yeah,
Sorry to interrupt you again, but Gonzalo Lesperger has a question as well for you.
yeah. Okay, well, go ahead.
Gonzalo, tienes que quitarte you have to unmute yourself. Well, I'll read it for you. Hello, very interesting the presentation, thanks. Do you have any FTTH example that you can share with us of E2E design/power budget with this type of splitters?
Yeah, I cannot. It's basically, I think, the same question as from, I think it was Marino, but the, so we cannot give, shall we say, right now, the power budget for actual deployments. So the asymmetric splitters are deployed, but there are two issues. The first is that in many cases we actually work with carriers through distributors, so that we're not making these detailed calculations together with carriers. We of course can do so, but often there's a layer in between us and the actual carrier that deploys it. And the second one is that there's also the question of 1/128, and also the fourth use case are actual RFQs that we were involved in where this came up. But we do know, for example, in the US with one customer, about 50% or so is now asymmetric, and especially for rural. So it has been, it's still on the rise, but there are cases where it's been deployed significantly. But if you have a particular question or situation, just shoot it to us, and we would be more than happy to do, an example calculation for you. Yeah. And so this is pretty much the summary here. And yeah, I hope that this will help you to solve some of the issues that you may wind up into. But again, if you would like to see how it can help you, just shoot us an email and then say, this is my architecture, these are the power budget issues, and what would you propose here? And then we will gladly do a calculation for you. Yeah, so for that, you can actually find us in Anga in case that you're going there. That's in 2 weeks down the road. Or you can send an email to the general email address or to my email address.